So here's a simulation from momentum, and we have two masses, one smaller mass and one bigger mass, and they're going to collide. And if you notice, they're both going at different speeds and different momentums. Okay, so, oh, and take note over here, this orange arrow, this orange vector, is the total momentum, like the total net force, because momentum is a vector. So, here we go. Boom. Okay, so if we bring this back up, see what happened. The momentum changed, and the speed over here changed. Well, everything changed. But it seems like the bigger mass's acceleration, the momentum decreased when it collided with the smaller mass, and the smaller mass's momentum increased when it collided with the bigger mass. See, it went a lot faster as it came shooting down. And let's just do that again, and let's look at the momentum diagram. So, okay, wait, a little smaller. Okay. So just take note of the orange vector. The total momentum did not change. It stayed put, stayed the same. But the initial momentums for each mass, those did change. Or maybe not the initial. Okay. So these do not represent the initial momentums, just before and after. Before the previous diagram, these vectors were in a different direction, and they also had different lengths. And then after the collision, the momentums for each individual mass change directions, and it changes direction due to the velocity, because according to our equation, momentum is equal to mass times velocity. Mass is just scaling, but the velocity vector is scaled by your mass. And because of that, the momentum and velocity both share the same direction. Okay, we'll look at Mr. Day's notes. Oh, here, before and after collision. Just what I explained, though. Well, we can look at first. The velocity vectors are toward each other because they're going in opposite directions, but they're moving closer together, the masses. And then after the collision, they're both almost repelling each other, so the velocities are in completely opposite directions. Oh, and no outside forces, because that's just that's our second law, that we cannot have any external forces, like, let's see, it could be air resistance, friction. We're just going to ignore that for our momentum problems for now. And here we're going to apply our third law to momentum. And so we start with the mass of object 2 and its acceleration, and then the mass and acceleration of object 1. And I think we have a negative sign because of the velocity vector. They're both going in different directions. So we symbolize that by putting a negative sign as in an opposite direction. And acceleration is also change of velocity over change in time. But for both objects, they collide at the same time, so there's no reason we could just cross that out. It's meaningless. And we keep going and going, and we interpret change in velocity as final velocity minus the initial velocity, and we distribute, and eventually we're going to end up with this equation. The final momentum of object 2 plus final momentum of object 1 is equal to the initial momentum of both objects, which means, if you remember, go back to our simulation, it means that this momentum vector, the net vector, it will not change because these will always add up to the same initial momentum even after the collision. Thanks for watching. Oh, this is Leanna from period 5.